Yeah, still I have to say good morning. So I'm not from UPC, so I'm a visiting researcher here at UPC, and I'm supposed to stay here for a few months. So I'm a researcher at a company which is called MsC, and is located in Portugal, in north of Porto. So the company is, it has something like 4,000 people working there, and has more than half century history. So the company is active in the field of transformer, high power and medium voltage and high voltage transformers, and also switchgear and automation steps, and doing some engineering contracts, and also it's active in the mobility, electrical mobility, including the railway transportations and also electrical cars. So moving to our main discussion, I just would like to highlight a few points about the requirement for multi-terminal HVDC grid, which is already highlighted by Juan. So why do we need to move toward the multi-terminal HVDC? I know that you will have more presentation on this maybe this afternoon, I don't know, tomorrow. So I'm just highlighting to give an idea, then move to the protection of these kind of grids. So as you can see, the offshore wind industry is moving strongly fast, and we have lots of installations in offshore areas since year 2007 till now. So we have 418 new offshore wind turbines installed in something like 12 new wind farms, and the installed capacity is now, it's about 2,080 megawatts altogether. So, but the problem is that here, especially I'm talking about Europe, we have the best locations for collecting the wind energy in the border of the continent, especially in the, I don't know if this pointer is working, yeah, in the borders of continent, especially in the northern part, and also we have the solar areas in the southern part. But the problem is that usually the main consumption sources and the main populations are living in the center of continent. So there are a huge amount of energy which is far from the population area, and we have a far distance, so we need to transfer this power. So as it is mentioned, mainly the solution is the HVDC, and okay, recently MsC HVDC. But this also will move us toward to have a multi-terminal HVDC grid, because especially in the northern area of Europe, in the North Sea, we will have lots of HVDC link, and then to have them stable and to make it possible to transfer and to share the energy between different countries inside the Union, we will have the multi-terminal HVDC grid, and it is a connection between different converters, and the connections can be cables or can be overhead transmission lines, depends on the location. But what is the, let's say, drawback of this technology? It's identified that this can be protection issues. The protection issues in multi-terminal HVDC grid is much more complicated than the AC one. Since I will introduce you the topologies of HVDC converters, I have here two figures. This is the conventional two-level MsC topology. So you have, you know that you have 3 arms, 3 legs, and then you have mainly 6 set of switches. But the problem is that when you have a short circuit fault here, depends on the grounding scheme of this transformer. It can be even a pole to ground, but mainly pole to pole fault. Because of presence of these anti-parallel diodes of IGBTs, the current will permanently flow to the fault point, and you are not be able to interrupt it. Even you block the IGBTs, the current will flow up. So It means that we don't have any control during the DC fault on converters. It's the same for the half-bridge MMC topologies. You can see each submodules, they have two switches mainly. So they have also anti-parallel diodes, and this means that after having the DC fault here, the current will flow again through the anti-parallel diodes and it will be uninterruptible. And the main point is that the characteristics of this DC fault current is again quite different from the AC one. In AC, the inductors will act like impedances. So because of the frequency that you have in your current, they can limit the current even in terms of rate of rise of current and in terms of the peak of current. But in the DC, we don't have such effect from the inductors. So after inception of a fault, suppose in the instance 1, we will have a rapid rise of DC fault current. If we have the fault very close to the converter, like at the beginning of a 100 kilometer DC line, we will have like within 1 millisecond it will reach to maybe 6 times of its initial or its pre-fault current. And if we have it at the end of that line, it will have a delay and a relatively limited peak, but then again within 1 millisecond it will reach to 3.5 times of its nominal value. So what are the remarks on protection of DC grid? Protection system should be simple, should be selective, as we have in AC grid, and should be effective. So in DC grid, selectivity will be a problem because you have, as I showed you, you have such a small period of time to identify the fault, which is not easy. Usually in the AC grid, our relays are relying on some kind of communications also between them to decide which line is really the faulty line. But in DC, it's not possible because the propagation of the fault current is much more rapider than the communication maybe. Or we can say it's with the same velocity. So selectivity will be a problem. And also you will have some kind of fault identification problems depending on the topology of the grid. But the main challenge will be how to interrupt this current. We have the circuit breakers in the AC system, but let's see if they will be useful for this kind of faults or not. So you can see a multi-terminal grid here again. It has four terminals and one terminal is supposed to be constructed. So we have different cables. So it's possible to have pole-to-pole or pole-to-ground or pole-to-pole-to-ground faults in the DC side of grid. Or it is possible to have some faults like short circuit faults, again with the same situation at the DC bus, which I would say it's the worst case. Or you might have some kind of internal fault in the converter, in the components like capacitors, IGBTs, and diodes, which can affect the DC side of converter. So these are the issues we should be aware of them. Then the characteristic of the fault current, and also when we are designing the protection system for the HVDC grid, we should be aware of the converter main circuit topology, DC line parameters, the anti-parallel diodes overload capability, also the IGBT surge capability. Also we should take into account the DC capacitors voltage limitation, as well as the DC grid stability, which implies to have a very fast detection and fast interruption. Also bypass circuit and fault current contribution. Here, if you suppose an AC current, and at this instance we insert a fault here, we will have the fault current which is increasing, but we have it crossing the 0 point. And if we open an AC circuit breaker, it will draw an arc, and after a few cycles, after crossing the 0 by current, because of having the opposite voltage of the arc, this arc will be quenched. So we are able to interrupt the AC, high LC fault currents within few cycles. But it's not like this in DC. In DC, we don't have the zero crossing point. So if we open a circuit breaker with the same technology from the AC, the arc will be drawn, but it is not possible to interrupt it. So you will have a permanent current even if you open the circuit breaker. So we have some kind of solutions in the literature for this, which is called HVDC circuit breaker. It is supposed that if we have an HVDC multi-terminal grid, we might have circuit breakers, HVDC circuit breakers at each end of the lines. It is not the final solution. You might have some other solutions to discuss it. Where should we put the HVDC circuit breaker? I'm not talking about this, but let's suppose this is the solution. And I want to give you an idea about the DC circuit breaker technologies more to activate your mind in this field also, which is one of the most interesting fields in the HVDC. So if we want to talk about HVDC circuit breaker, we should take to account the mechanical circuit breakers, we should take into account the solid state circuit breakers, and we should take into account the hybrid circuit breakers. The mechanical circuit breakers for HVDC technology is not a new thing. We have it since 1988 which is developed mainly for CSC HVDC technologies or thyristor based. But okay, we know that they have not been used there because all the connections were point-to-point connections, so it was possible to interrupt the fault currents from the AC side, and the CSC technology, despite the VSC one, is not so vulnerable against the DC faults. So this technology has an operation time like less than 60 milliseconds. It's ready for quite high voltage and good current, 4K amps. It has a low power loss because you have mainly a mechanical breaker here. So this is a metallic contact, so you have a low power losses here. And the principle of operation is opening this breaker and imposing an oscillating current, which is opposing the fault current and pushing the fault current, the summation of the fault current and the opposing current to cross the zero. And after that, we can quench the current. Then we have another technology, which is again from the same time almost, 1972 till 1984, and it is active mechanical HVDC circuit breaker. And here you have the some other kind of topologies which are attached to these mechanical breakers. And usually you have this capacitor charged with this circuit, and then you will be able to quench the current in the mechanical breaker in less time, which I would say it's less than 40 milliseconds. And the other things are almost the same. But I think one of the most interesting topologies for HVDC circuit breaker, which has been introduced in 2011 by ABB, is the hybrid breaking concept. So you have this mechanical disconnector here, which is supposed to be a fast mechanical disconnector, and you have small size IGBTs here. Then you have a full solid state breaker branch, which is ready for interrupting the full fault current, and you have a surge arrestor branch, and you have a fault current limiter inductor here. So the operation is that the normal operation, you will activate this branch, so the current will flow through the mechanical breaker and these IGBTs. And when you have a fault, you will commutate the current to this branch and you will interrupt by this. And the energy which is released from the inductor of the cables and also the interruption, the switching, will be damped inside this surge arrestor, which are usually metal oxide varistors. So you have another technology, mainly I think it's from Alstom. So this is like, the concept is almost the same as the previous one. But instead of having the full solid state branch relying on IGBTs and having the surge arrestor in parallel with that only, you will have the main branch, and then you will have thyristor based dampers, and finally another surge arrestor here. So just to highlight that, the operation time for this kind of breaker is identified to be less than 3 milliseconds, which is quite good for multi-terminal HVDC grid protection. And for this one is around 5 milliseconds, which it is again almost good. But if we have other solutions much more faster than this, it will be better, because we will save our converters and other vulnerable components rapidly. So the other technologies which the research is going on there are the solid state technologies, which they use the IGBTs or thyristors or this kind of switches instead of mechanical one. But mainly the problem with this kind of switch topologies is the power losses, because you have a relatively higher power losses inside the semiconductor devices. And it's not comparable with the mechanical ones. But since the semiconductor technologies are also improving at the same time, it can be seen that in future maybe this kind of topologies will arise and will be employed to protect this kind of grids maybe. So you have different kind of topologies for solid state one. And these are also from that. And these two simple topologies, which are the same as the conventional solid state topologies, they are using the wide band gap semiconductor switches like SiC based switches, and this switch is supposed to have a higher band gap, so they will be ready to withstand under higher voltage with the single chip, so you will have less power losses, and they seems to be attractive also. Let's see what is one of the main issues regarding the breaking and interrupting the current. Because if you have, for instance, the solid state switches like IGBTs, you put them in series to be ready to withstand under the nominal voltage, you can interrupt the current. But what is the main issue with that? The main issue is this. If you suppose this circuit, this is a simple demonstration of a DC source, a load, which is connecting these impedances, which is supposed to be like DC line, simple model, which has a resistance and inductance. And you want to open this switch, which is, you can think about it, IGBT, set of IGBTs. What's happening there, if you write the equations for the short circuit current and also for the voltage across this breaker, like this, you will see that when you try to interrupt this short circuit current within a short period of time, because the IGBTs are so fast, so they like to interrupt any current. If you turn them off in less than, you can think about in less than 1 microsecond even, 2 microseconds. So you will have a very, very small DT here, and you have a large DI here, because we are talking about the short circuit current, and you are pushing the current to become to be zero. So you will have this term positive, and it will add up to this VDC. So you will have a high voltage, high transient voltage across your breaking device. So if you're supposed to design your device for 320 kV, it might be exposed to 1000 kV during the switching, and it will be destroyed. So the solution for that, as I showed you, is to put surge arrestors like this to damp this voltage, this current. And if you try to identify, to start the fault interruption process faster, like this, like this yellow curve, this is the fault current, is going up, and we start the interruption here, so we will have less transient voltage. But if we have a delay in interruption, starting the interruption process and interrupt like this, we will have larger transient over voltage. Or if we try to interrupt the current, suppose from here, within a very short period of time, very fast, we will have again very, very large over voltage. But if we try to interrupt it slowly with some solution like the surge arrestor, which is doing like this, it's increasing the DT, so we will have again less over voltage. let's move to one of the works that we have done in at FSEC and also University of Porto. We are doing some research on solid-state circuit breakers. So we have introduced a topology of solid-state circuit breaker. We are employing the IGBTs like this, but only in one direction, which is again important because if you have the IGBTs in one direction, it is supposed to have the current flowing through one terminal to the other terminal. So to compensate this problem in the other kind of topologies that I showed you, like the hybrid one, you have the IGBTs which are connected in anti-series, let's say, configuration. It means that you have couple of IGBTs which are forming the cell. So you have inside each cell, you have a couple that they are looking to each other from the emitter side. So you have the emitter of IGBTs are connected to each other. So you can have the current flowing in both directions to have a bidirectional switch. But we use only in one direction IGBTs. So we have a current limiting inductor here. We have this circuit here, and this is a capacitor. So if I want to show you how we integrate this topology to a asymmetric monopole HVDC configuration, it will look like this. You will have the converter here, you will have a breaker here, you will have the cable here, and you will have a breaker here which looks to the opposite side. All the emitters of these IGBTs are looking to the cable, and all the emitters of these IGBTs are looking to the cable. So the operation principle, we are charging this capacitor through this branch by triggering this thyristor. After having it charged up, we are closing the breaker main branch, and we have the current which is flowing, if this converter is supposed to be rectifier, is flowing through the IGBTs and the cable and through the anti-parallel diodes here to the other converter. So you can see that the bidirectional current flow is maintained, no problem. And you can change the current flow again. I mean, the current can flow through these IGBTs and this cable and these anti-parallel diodes. So the bidirectional current flow problem is also solved here, but with use of half of IGBTs. Half of IGBTs means half powerless and half maybe investment cost in terms of implementing that branch. So during the fault, what we are doing, we are triggering this thyristor, which is connected to this pre-charged capacitor, to the nominal voltage of the grid. So we have some kind of nominal voltage which is connected to this point, and it will prevent this voltage of this point from dropping because of the interruption that we are going to do, and because of these inductors, inductor of cable and this fault limiting inductor. And then somehow we will open these IGBTs very smoothly without very, very high surge voltage. So the IGBTs and the braking device will be safe. And after a while, this current through this capacitor will discharge to the fault point, and this thyristor will be turned off naturally. So just to show you how it works, I have a model here, which is modeled mainly in PSCAD. So we use the frequency-dependent model of cable. We implemented the model from these physical dimensions that we have here. So the voltage rating is plus minus 320 kV, and the configuration is symmetric monopole configuration of HVDC. So we can integrate the same circuit breaker to any kind of configurations of HVDC, like asymmetric and symmetric monopoles or bipolar configuration. So if I want to show you this current which is flowing from this converter, each converter from the positive pole and the negative pole, you can see that after introducing the fault, we can interrupt the fault current very, very fast from the converter. So converter will not be under so much high pressure. So we have the voltage across each breaker here. So you can see it's quite in an acceptable range. For 320 kV, we have something like 30 kV of transient voltage, which is quite normal, and we can have even more than that. and there is no problem. So here we can see these currents, which are the currents flowing through the cable. So you can see the peak out current in the cable, it's higher because we have the pre-charge capacitor which is connected to the fault point, and the fault current is damped slowly in the cable. But in fact, the breaking operation has been done so much faster, as I showed you, and this is done isolated from the converter and inside the cable, and it has no impact on the converter. So just as a conclusion about the last part of the discussion that I introduced you, with this topology we may be able to decrease the transient over voltage very effectively without using the parallel surge arrestors, and it is expected to have less power losses. As I told you, we replaced a couple of IGBT with one IGBT, but this is not this idea is not from us, so it is adapted from some other applications to this application. But the main idea that we have developed is this branch. So we have this is the conventional topologies for solid state circuit breaker. You can see you have the parallel surge arrestor branch. So when you are opening this, this current is still flowing through this parallel branch to be damped. So if you suppose the interruption curve for current for these topologies, like this blue one, for this topology that I introduced you, it will be like this one. So it's much more faster even from the conventional solid state circuit breakers in terms of isolating the fault current from the converter. So I don't want to take your time much more than this, but if you have any questions, I don't know, you can ask now, or I don't know what is the plan, Eduardo?
No,
at the end.
If you have any question to add,
okay. The slide, 2 slides before, there was a positive and negative sequence pole current.
This?
Yes, yeah, but these are not symmetrical ones, positive and negative pole.
Okay.
Yeah,
Here,
here.
you are talking about this, and you say that maybe why?
Yeah, exactly.
Yeah, why?
It's not
For instance, the negative pole is not exactly the same as the positive pole. Yeah, actually you are right, and this is I think mainly because of the model that we have implemented here. So we identified that, and we think that about the negative pole there are some kind of differences with the positive pole. I think maybe like one mistake in terms of adopting the dimension for the negative pole, and it's mainly because of that. You are right, but it usually should be symmetric because you don't have any other difference there. So, any more questions?
Is it applicable today with all methods? I mean, are obviously all of these methods used in real life, or are they just only on this study case?
I couldn't get you.
I mean, that
If they are real.
are these methods used today already?
No,
Are
no. You don't have any DC circuit breaker actually working, I think, in operation. Maybe I heard that in China they want to integrate one HVDC circuit breaker to a 3 or 5 terminal grid that they are going to. I think they have the 3 terminal, so they are going to have the 5 terminal one. But you don't have the HVDC breaker working in operation. So these are new technologies that we are talking about. And actually, even I cannot predict which one is going to be applied in future. But mainly, it seems that if we want to have a technology which can be adapted to HVDC grid, it would be hybrid HVDC circuit breaker technology. But today, when we are talking now, there is no requirement to have this in operation because we don't have such a multi-terminal grid. And this is a matter of business also, because we cannot have one topology. You know, it's a kind of we should think about a kind of interoperability in future. If we are supposed to see the multi-terminal HVDC grid, we might see also different HVDC circuit breakers, as we can see different converters. So because the HVDC leaders, each one are developing and introducing their approaches to this. So it's not like, to select one topology. You should think about all of them. So, thank you.
Okay.